Everybody, this is Mr. Folly, and welcome to Equilibrium. The next 3 chapters, believe it or not, are equilibrium, and the nice thing is it doesn't change a whole lot, but you start to really appreciate the ease of this chapter, which hopefully is pretty straightforward as it becomes more and more complex. So we're going to do definitions of equilibrium with graphs, one-way reactions versus equilibrium reactions. KEQ is a mathematical equation we're going to learn. Temperature is the only way to change K. If K is greater than 1, what does that mean? If K is less than 1, what does that mean? Examples of writing K expressions, and solids and liquids are not involved, and why. That actually goes right there. So let's hop into it. Equilibrium is a dynamic chemical system where the rate of the forward reaction equals the rate of the reverse reaction. That means it doesn't stop. No stopping. Our classroom is an example. So, for example, room 313 has 24 students in it in the first hour. Then the bell rings, and then what happens is, in second hour, there's 24 students in there, but they're different students. So the red students would be, I don't know, whatever science class is in their first hour. The blue students, this is you. Now, you have to admit, you're not the same people as the first 24 people in there. And then the bell rings again, and there's a different 24 people come in, 24 people come out, and geology's in there. And those are different people than you. The bell rings again, a different class is in there. So what happens is they're always changing, but the rate of people leaving equals the rate of people coming in. And it's quite possible that someone could be in AP Chemistry and then Geology right afterwards. It happened a couple of years ago. So it's possible that the same people stay, but generally they're changing all the time. So it's very dynamic. The way you look at this graphically is if I'm looking at CO, or this would be and H2O, you start off, this is a reactant because there's lots of it. This is a product because there's none of it. And notice starting off, the rate is very, very fast. The rate would be the slope. And then here, the rate is 0. That doesn't mean that nothing's happening. That means the rate is the same. So that means every time a CO dies, a CO2 is born. And of course, that would be an extreme. They don't really die and they're not born, but you get the idea. So the definition of equilibrium is the rate of the forward equals the rate of the reverse. So if instead of graphing the amounts, I could graph the rates, notice the rate is very negative, the rate is quite positive, and eventually equilibrium is where the rates are the same. There are 2 main types of reactions. This is a one-way reaction. It goes to completion. These things, so for example, NaOH, solid, drop it in water, makes Na positive aqueous plus OH negative aqueous. This happens one way because it is strong. Weak ones, we know, do not dissociate 100%. So these are mostly strong acids and bases and combustion in chemistry class. There are other examples of one-way reactions, but in general chemistry, that's it. The other examples would be like dying. I ran over a possum. There's not an equilibrium for a possum. That possum dying, and then, oh, look, at 10 o'clock, he's living again. Oh, noon, he gets hit again, he dies. Oh, 2 o'clock, he comes back to life. No, we don't have zombie possums that come back and forth like that. But really, the one-way reactions are dissolving strong acids and bases and then combustion reactions. And combustion reactions are not going to reverse. You're not going to be able to collect your CO2 and H2O if you're burning gasoline and get it to go back into gasoline. Equilibrium reactions, there's 3 basic types. These are much more common in this class. Again, equilibrium means 2 opposite reactions at the same time, which is this double arrow. If I'm drawing it by hand, often do that. Dimerization. We've used this dimer an awful lot. So NO2 and N2O4. Remember, NO2 has a single electron on it, so it looks something like this with a single electron. And then that single electron, of course, is the key to the dimerization because single electrons want to react very much. Dissociation of a weak electrolyte. So if it's a weak electrolyte, like a weak acid or a weak base, which is the most typical, this is a weak acid, the dissociation doesn't happen 100% and stay there. So some of the acetate ions would react with H3O positive and form water back the other way. Saturated solutions, if I have silver chloride, sugar, and chlorine, what happens is, so I like to think of this as like iced tea. So if I've got solid particles here, I've got too much in here in my iced tea. What happens is I also have some red particles that are dissolved. And some of these particles will precipitate out, and some of the precipitate will dissolve. So that's an equilibrium process where it's going back and forth. If I'm just looking at it, I would see, say, 1 million precipitate particles, and that wouldn't change. But if I talk about the individual identities, if I say this, this sugar particle right here is Amanda. Right now, Amanda is aqueous, but then she's going to turn into a precipitate. So what's the equation for K? We talk about these equilibrium constants. K equals products over reactants raised to the coefficients. Now, if you remember when we did kinetics, we said don't use the coefficients, don't use the coefficients. But we did use the coefficients if it was the, there's the kinetics part. We did use the coefficients if it was the slow step or if it was the equilibrium step. Well, guess what? This K is the equilibrium K. So it's just products over reactants to the coefficients. Okay, and really it's going to be the concentration of them. So in brackets, brackets means you are in molarity. So K is products over reactants. KEQ is temperature dependent. Forward and reverse reactions are temperature dependent. And if I asked you kinetically, why? If you have a higher temperature, you're going to have more effective collisions, so rate tends to go up. And we'll talk about that next podcast. If K is greater than 1, remember K is products over reactants. If K is greater than 1, that means you have lots of what? Products, right? So if this is big, this is tiny, K would be greater than 1. So you have lots of products. This is great if you're if you're trying to design an equation to make a product. So if you're trying to make the drug that cures cancer, you want to have a very high K because you'll make a lot of products and it'll use up the same reactant. So at equilibrium, you'll have more products, but the rates will still be the same. Okay. If K is less than 1, remember K is products over reactants. If K is less than 1, that means reactants have to be bigger than products because that's the only way you can get a K of less than 1. But again, at equilibrium, the reactants are bigger than the products, but the rates are still the same. Here's an example. This is table 13.1 in your book. It has different initial concentrations. A bunch of different initial concentrations. Some of them even switch the reactants and products. And then you wait until the reaction reaches equilibrium. And when that happens, you just do products over reactants, right? So if my reaction is N2 plus 3H2 yields, so it's N2 plus 3H2 yields 2NH3, K would be products over reactants, NH3, concentration squared, over my reactants, this should have a yield sign in it, N2 to the first, and H2 cubed. That's it. Now there's one trick to this. Concentration of pure liquids and solids are not included in equilibrium expressions as their concentrations are themselves constant. So for example, if I ask you what's the molarity of pure water? Well, molarity is moles over liters. Well, isn't that kind of like moles would be mass over molar mass over volume? And that's basically the density of water, which is a constant. So liquids and solids, basically you're talking about a density, which is a constant. So what happens is those things are incorporated into the K and the K expression. So your equilibrium constant includes those. So they're not included in equilibrium expressions as they are constants and not variables. All right? You don't have a bunch of different constants In an equation, you have one constant, or you combine your constants, and you're only worried about the variables. Write the K expression for these guys. K equals NO2, NO2 products squared over reactants N2O4, the dimerization reaction. Here is acetic acid. What would the states of matter of these things be? By the way, an acid, to be an acid, is always aqueous. Water is a liquid. Ions are always aqueous for our class. So I can ignore water because it's not going to be part of the equilibrium expression. So K is products, CH3, COO negative to the first times H3O positive to the first over CH3, COOH, and that is aqueous. That's it. K for a dissolving equation is a little bit different. It's just Ag positive, Cl negative. And if you put this down on the bottom, it would be a constant, which, if it makes a constant, which I'm going to call C, right? That constant I can multiply times that constant and just say, oh, that's already a constant. A constant times a constant is a new constant. So then we're going to just call it Ag positive times Cl negative. And it's over 1, but don't show that. It makes it look like you took math in Alabama. The value of KEQ may appear to be change based on the way the equation is balanced. So instead of writing 2 and 1, I could do 1/2 and 2. But what really happens is this can be, they are not different. The reason why they're not different is K fixes it. It may not seem like it would because you're square rooting things or cube rooting things, but it really does. And mathematically, you can do a proof showing that. But I'm really not going to. You can just know that balancing would not, the K would change, but the ratios and things like that are not important. If KEQ is greater than 1, I already did this. Sorry. Reactions have a forward and reverse or review already. How about that? So reactions have a forward and reverse directions for most cases. And the exceptions you should know. Equilibrium is where forward equals reverse, and it's all about the rate. K is temperature dependent only. Nothing else changes it. Nothing, nothing. Solids and liquids are omitted from K, and K equals P over R using coefficients. I feel like I've forgotten something, so I'm looking at my front page again. That's it. So have a good one. Toodles.